So hello everyone. The first speaker of today's morning session is Jake Solomon from Hebrew University. So he's going to talk about the degenerate special Lagrangian equation, the Lagrangians with boundary.
Okay. First of all, thanks very much to the organizers for inviting me to speak here, and want to wish Professor Tian a very happy birthday. So actually, this project, I think was like the kernel of the idea for this project was suggested to me when I was a PhD student by Professor Tian, and took a lot of time until it actually developed, but it's still developing. Just maybe present a sort of progress report. So the setting is that we have a Calabi-Yau manifold, or an almost Calabi-Yau manifold. I think this is a typo, it should say almost Calabi-Yau manifold. Let's see. Right, so that means that X is a two-dimensional manifold, a 2n-dimensional manifold, and J is a complex structure. Omega is a Kähler form, and capital Omega is a non-vanishing holomorphic N0 form. And we have G, which is an associated Kähler metric. Okay? So the Calabi-Yau condition, which turns this from an almost Calabi-Yau manifold into an actual Calabi-Yau manifold, is that this equality of differential forms holds. And if that holds, then the Ricci curvature of the Kähler metric is 0. And this condition is not necessary. It's sufficient for us to have an almost Calabi-Yau manifold, but assuming the Calabi-Yau condition, we'll simplify the formulas. I'm going to do that. So we can look at Lagrangian submanifolds of a Calabi-Yau manifold, and there's different types we want to distinguish. So it just means that you have a submanifold of dimension n, and it's the symplectic form when you restrict it is 0. So then, in addition, if you have the real part of the holomorphic volume form restricted to the Lagrangian L positive, so I'm going to assume that the Lagrangian is oriented. So if the restriction is positive, so then we call this Lagrangian positive. Okay, so that's what I mean by positive Lagrangian. And doesn't have delay here. So it's special if, in addition, the imaginary part when restricted to L is 0. So in general, the real part of the holomorphic volume form is a calibration. So it's somewhere, it's always going to be less than or equal to the volume form. But if we take the imaginary part equal to 0, then it's going to be actually equal to the volume form, which is the calibration condition. So you can always change around your holomorphic volume form, and you can replace, capital omega with, say, I times capital omega, and then you can sort of interchange the roles of the real and imaginary parts without losing anything, and so we call that an imaginary special Lagrangian if we sort of switch the roles of imaginary and real here. So I think like a important problem about special Lagrangian submanifolds is the following, that if I'm given a Lagrangian L, we want to know when you can flow this Lagrangian by a Hamiltonian flow until it becomes a special Lagrangian. And if you can, then is that special Lagrangian unique? So as far as uniqueness, there's a fairly satisfactory result, which is that if the Floer cohomology is well defined, meaning that it's unobstructed, then if there exists a special Lagrangian, it must be unique in its Hamiltonian isotopy class. So then the question about existence is a bit more difficult. So there's like a sort of conjecture due to Thomas and Yau, which says that under appropriate conditions, you can take any Lagrangian and flow it by Lagrangian mean curvature flow, and eventually it will break apart into a sort of connect sum of special Lagrangians of different angles. Okay, so this is a kind of a answer to the main question. I mean, if it were to be proved, but it's pretty difficult to prove. There's lots of examples of finite time singularities under all kinds of assumptions for the Lagrangian mean curvature flow. And also you have to sort of refine this picture to take into account sort of floor theoretic obstructions, and presumably you also want to take into account like Bridgeland stability on the Fukaya category. That's, you know, an obstruction to the sort of approach using Lagrangian mean curvature flow as proposed by Thomas and Yau, and later refined by Joyce. Another way of looking at another way of approaching the problem, the main question of trying to find special Lagrangian submanifolds, is to say just use the direct method. So you take some you know, Hamiltonian isotopy class, and you just choose a sequence which minimizes volume. So what does that have to do with special Lagrangian? A special Lagrangian minimizes volume in its homology class. So you should be able to just find them by trying to minimize volume. But this runs into some problems because, well, it still seems good because, you know, if you have a smooth Lagrangian minimizing volume among Lagrangian competitors, so it has to be special. But the trouble is that the sort of, if you do the direct method, you find some kind of perhaps singular, maybe an integral current, which minimizes volume among Lagrangian competitors, then it might not be special. So there's like explicit examples of this happening due to Wolfson. The idea is that we should try to find, you know, maybe a different functional and a different space to minimize, and then in order to try to find special Lagrangians, that's sort of the starting point of the project that I want to discuss. So let's look at a Hamiltonian isotopy class of positive Lagrangians. So the idea here is to, instead of looking at all Lagrangians, restrict to positive Lagrangians, and then try to use the geometry of this space of positive Lagrangians to make some progress on this question of existence of special Lagrangians. So what do I mean by a Hamiltonian isotopy class of positive Lagrangians? So let's fix one closed positive Lagrangian, and then look at all the other Lagrangians which you can move this fixed Lagrangian to, lambda star, by a Hamiltonian flow on your ambient Calabi-Yau manifold X. So you just look at all the lambdas such that the time one flow is of the base lambda star is lambda, and then, but all along the flow you stay positive. Okay, so this is what I mean by a Hamiltonian isotopy class of positive Lagrangians, O. And we're going to try to minimize some functional on this space to find special Lagrangians. So first of all, this O, this orbit, is a Frechet manifold. It's an infinite dimensional manifold. And we can also say what the tangent space is. So if you choose a positive Lagrangian in this orbit, so the tangent space is given by looking at functions on lambda. The tangent space to the whole orbit is given by looking at the functions on lambda which have integral 0 with respect to the the real part of the holomorphic volume form, which we should assume by definition of positive Lagrangian, that this real omega is a volume form on lambda. So it makes sense to look at this as kind of a normalization condition. Okay? So the idea of this is that sort of like changing in a Hamiltonian isotopy class should be given by like flowing by a Hamiltonian function. But all you need to know about the Hamiltonian function is its restriction to your Lagrangian to know how the Lagrangian is going to change. So you just look at functions on the Lagrangian itself. That's the tangent space. Okay? So we're going to define a Riemannian metric G on this orbit O by sort of an L2 metric formula. So it's like a bilinear form, taking a function on lambda and another function on lambda, and just sending it to the product of the functions integrated on lambda with respect to this natural volume form real omega, which comes from the definition of positive Lagrangian. Okay. So one theorem which was proved is that so I mean, a priori, G is like it's a weak Riemannian metric. It doesn't necessarily have a Leibniz-Shivda connection, but in fact, it does. And moreover, you can calculate the sectional curvature, and it's non-positive. Moreover, there's let's consider the universal cover of this orbit O. So this might not be a big difference. I mean, it's reasonable to conjecture that maybe this is just a diffeomorphism, but it's probably really, really hard to prove that. But let's suppose you have the universal cover. There's a functional C on the universal cover, which is strictly convex along geodesics of the metric we just defined. And moreover, the critical points of C lie over special Lagrangians in O, if you look under the covering map. Okay? So in particular, if you knew that O was geodesically connected, you'd immediately get the uniqueness of a special Lagrangian if it exists. Okay? Also, I should mention that when you look at the Euler-Lagrange equation of C, it's the special Lagrangian equation on the nose. So if you could try to set up a direct method approach, you'd have a better chance maybe at getting actual special Lagrangians as even if you had like a singular minimizer, you might have a better chance of proving that with special Lagrangian than with the volume functional. But that's a hard problem. Okay, so this is kind of a motivation for looking at this space of positive Lagrangians. So we have one is just looking for special Lagrangians, but there's another motivation which has nothing to do with special Lagrangians, which is more like kind of classical symplectic topology, which is that supposing you have two positive Lagrangians which are connected by a geodesic, then there exists a function. This function will turn out to be like sort of the velocity of the geodesic, such that there's a function on one of these Lagrangians such that the number of intersection points of a Lagrangian is bounded below by the number of critical points of the function. So the Arnold conjecture was mentioned in Guangbo's talk yesterday a bit, like a homological version. But in fact, I think Arnold's original conjecture was that the number of fixed points of a symplectomorphism should be something like the number of critical points of a function. And here, like intersection points of Lagrangians is closely related to that. Okay, so in fact, if the Lagrangians intersect transversely, then we can take this function to be a Morse function. Okay, so this is just another motivation for studying positive Lagrangians and their geodesics. So now I'm going to try to go a little bit more into what these geodesics are. So, because sort of that's the key to what we were discussing before. Well, let's suppose we have just some path in our orbit O. So let's choose a family of diffeomorphisms from some fixed manifold L to lambda t. Okay, so just a parametrization of all the submanifolds lambda t in our path from a fixed abstract manifold. Okay, so now we can define the time derivative of our path. So that's going to be a function on lambda t, because that's what the tangent space to our orbit is. It's just functions on the Lagrangian we're considering. So the time derivative is a function such that when you contract the time derivative of this diffeomorphism with the symplectic form, you get the exterior derivative of this function composed with the parametrization. Okay? So this actually, it looks like it depends on the parametrization, but it doesn't. It just gives you a well-defined function on lambda t. Up to, well, I mean, there's this normalization which has to do with the integral, but okay. So another thing which we're going to need to talk about geodesics is the notion of a horizontal lift. This is going to be something like parallel transport along a path with respect to the Levi-Civita connection. So this parametrization psi t is going to be called a horizontal lift of the path lambda t if, when you contract its time derivative with the real part of the holomorphic volume form, you get 0. And it's an easy thing to show that such horizontal lifts always exist. That's the existence of the Levi-Civita connection. Okay, so now we can say what a geodesic is. So a path is a geodesic if and only if, for any horizontal lift psi t, this parametrization, which is kind of like parallel, the time derivative ht, which we just defined, this function satisfies, it's just constant with respect when you parametrize your Lagrangians in this way. Okay, so that's what a geodesic is. Now, that's kind of a very geometric approach to saying what a geodesic is, but I think it's helpful also to see things like in like a Euclidean setting where you can write down sort of an explicit PDE. So, sorry, there's one more thing I wanted to say about this, which is that since this composition is time independent, we can just call it the time independent Hamiltonian of lambda t. Okay? So it's interesting, like, this isn't like a time, I mean, this is a function ht on a varying set of domains. So in a sense, I mean, it's a little bit strange to call it time independent, but since you have a uniform parametrization of all different domains, it's still reasonable to call it time independent. Okay, so let's go to now the Euclidean case and see what things look like in terms of PDE. So let's consider just our Calabi-Yau manifold to be just a complex n-dimensional space. And let's look at an open bounded convex domain with smooth boundary in Rn. And we'll look at some function ut on this domain where t runs between 0 and 1. That's going to be our path. How do we get a Lagrangian from that function? Well, we just take the graph basically of the gradient of the function. That's going to be a subset of Cn, and it's going to be a Lagrangian submanifold. And the claim is that lambda t is a geodesic if and only if the function u of t and x satisfies this equation. So you have here like the determinant of, this is supposed to be like the n by n identity matrix, but where you append sort of like an extra row of zeros in the first column. Okay, so then you have this n by n matrix plus another n by n matrix. This is the space-time Hessian of u times I, and you take the determinant and you take the imaginary part, and that's supposed to be equal to 0. Okay, and plus you have to have the positivity condition, which is like being a positive Lagrangian. Okay, so this is called the degenerate special Lagrangian equation, and that's because we proved that with Yanir that the DSL is a degenerate elliptic PDE, and it admits a certain type of viscosity solution under appropriate boundary conditions. Okay, so now I want to talk about a more like geometric way of trying to find solutions to the degenerate special Lagrangian equation. So let's suppose we have a geodesic in the space O. Lambda t is just a family of Lagrangians, which is a geodesic. Okay, so now we choose a horizontal lift, this nice parameterization, and we let H be the time-independent Hamiltonian, because it's geodesic, it has such a time-independent Hamiltonian by definition. Okay, so now for each real number C, we can look at basically the level set of the Hamiltonian, okay, and then just take it times an interval 0, 1. And we want to, remove the critical points to avoid singularities. Okay, and so this is what we call a cylinder. It's just like some manifold times an interval. And we can define a map from the cylinder into our Calabi-Yau manifold by just sort of like taking this level set and letting it flow along the geodesic. Okay, so this psi t of p is just saying like, where does this level set of the Hamiltonian go at each time along the geodesic? Okay, and we can also define a function on the cylinder to just look at the time coordinate along the cylinder, okay? And so the theorem is that, this is joint with Amitai Yuval, former PhD student of mine, that first of all, this map phi c from the cylinder into the Calabi-Yau manifold, which sort of parameterize the level sets, the Cth level set of the Hamiltonian as it moves along. So this thing is an imaginary special Lagrangian immersion. And moreover, the time function along the cylinder is a harmonic function with respect to the natural pullback metric. So the picture you get is like this. So if these blue curves are sort of like, so here's lambda 0, and here's lambda 1, and then in between you have like lambda t moves up and down. Okay, so these red lines which go in the vertical direction are meant to represent sort of imaginary special Lagrangian cylinders which have boundary on the one hand in lambda 0 and on the other hand in lambda 1. Okay, and you can tell how lambda t moves along these cylinders by just looking at the level sets of these harmonic functions, which, I mean, if you say, I give you a cylinder and ask for a harmonic function which is 0 on one end and 1 on the other, there's a unique such harmonic function. So I can just take my cylinder and compute how the geodesic moves along it by solving the Laplace equation. Okay. Now what about these imaginary special Lagrangian cylinders? Like, how do they behave? How many should we expect to find in general? So let's just look at a general situation where we have like some arbitrary n-1 dimensional manifold, which is like a level set of a function on a Lagrangian. Okay, and then let's look at two positive Lagrangians, lambda 0 and lambda 1. Okay, so then we can look at this space of all the possible imaginary special Lagrangians which are like modeled on a cylinder 0, 1 times n, okay, with one boundary component in lambda 0 and the other boundary component on lambda 1. Okay, so there's a theorem which says that if the manifold which you take the cylinder on is closed and connected, then the moduli space of special Lagrangian cylinders modeled on that manifold is a smooth one-dimensional manifold. Okay, it doesn't matter what the topology of n is, you always get a one-dimensional family of such things, which is just what you expect from like level sets of a function. They're indexed by the level of the function. Okay, so then we can define a cylindrical transform of a geodesic, which is, let's suppose we start with okay, let's just say, look at the union of all the possible moduli spaces of imaginary special Lagrangian cylinders running between lambda 0 and lambda 1, but now allow the topology of the cylinder to vary. So, and now take a geodesic in O and look at what we call the cylindrical transform. It's just going to be all the possible cylinders going between lambda 0 and lambda 1, which appear these kind of traces of level sets as you move along the geodesic. Okay? So that's what we call the cylindrical transform. And the idea is that you should be able to reconstruct the geodesic from the cylindrical transform, and this should give you a way to produce geodesics. Okay, so let's see how this works in practice. So suppose you have, now I'm going to make some simplifying assumptions. I don't think these assumptions are necessary, but as sort of a first stab, this seems like a reasonable thing to do. Let's assume that we have transversely intersecting positive Lagrangian spheres. We're going to make the topology as simple as possible. We're going to assume they only intersect in 2 points. And then there's a one-to-one correspondence between what we call regular components. You can just say what this means in a precise way, but I don't have enough time now. So you can look at components of this moduli space of imaginary special Lagrangian cylinders on an n-1 sphere that run between lambda 0 and lambda 1. You look at components of this, which satisfy some regularity criterion, and that's exactly going to be the same thing as cylindrical transforms of geodesics. Okay, so you can basically characterize the image of the cylindrical transform so you can actually invert it. Okay, so once you have this in hand, well, the special Lagrangian equation is elliptic. So when you change the endpoints of the geodesic in the situation of the preceding theorem, what you can see is that the geodesics kind of deform along with changes of the endpoints if they're sufficiently small, and they deform uniquely with C2 alpha small deformations of the endpoints. So now sort of those positive Lagrangians which can be connected with geodesics form an open, in the C2 alpha topology, subset of all. So a concrete application of this theorem is the following. So let's suppose you take a polynomial in one variable of degree m plus 1. You can then assign to that an n-dimensional affine algebraic variety, which is called the AM Milnor fiber, n-dimensional AM Milnor fiber. So this is given by the following equation, and this should say Cn plus 1, sorry. And the Milnor fiber has an action of the orthogonal group, which just acts on the first n coordinates here in the obvious way, matrix multiplication. So here you can say that Hamiltonian isotopy classes of the ON invariant positive Lagrangian spheres are geodesically connected. So basically, if you have two ON invariant positive Lagrangians, you can always connect them by a geodesic of ON invariant positive Lagrangian spheres. So these guys are found by essentially solving an ODE. You can reduce by this kind of symmetry to an ODE problem. Then you can ask, okay, I found these solutions using an ODE. Do there actually exist sort of genuine PDE type solutions which don't satisfy any extra symmetries? And the theorem we just said says that, yeah, you take any of these ON invariant geodesics, and you do a little perturbation to one end, you of course kill all the symmetry, and you still have geodesics there too. Okay, so another thing which you know is, suppose you don't have any geodesic to start with, but you want to make a geodesic. Well, there's a way to generate like imaginary special Lagrangian cylinders just a priori. So how do you do it? You take two positive Lagrangians, and to each intersection point, you can assign what's called the Maslov index. It's important in Floor homology. Now, suppose you have an intersection point which has Maslov index 0 or n. So this should correspond to either a minimum or maximum of the Hamiltonian function. And then there exists a family of imaginary special Lagrangian cylinders converging regularly to this P. So it's basically going to be like if you imagine there was a Hamiltonian function generating a geodesic between lambda 0 and lambda 1, then its level sets would be these spheres as n minus 1s embedded in the lambda 0 and lambda 1. And here you can say that actually there exists a family of special Lagrangian cylinders which just behave that way, always, without any condition. And the question is, okay, so this is how it looks. If you have two Lagrangians, lambda 1 and lambda 0, and you have some intersection point of Maslov index 0, then you have these sort of like cylinders nearby which kind of converge to this intersection point. So I think I'm out of time, but yeah. So let me just go to the most important slide. Oops. Happy birthday to Professor Tian.
Thank you.
Okay, do we have questions on the audience?
So what, I guess you missed a few transparencies. You try to, things overlast the few transparencies.
Thanks. So I think yeah, so if there's I had some questions also, but let me just go to like something which is relatively new. This is joint work with Asaf Kapota, a PhD student of mine. So if you have a closed Lagrangian submanifold M, so you can look at this sort of space of positive Lagrangians with boundary in M. So let's choose like lambda star is going to be a positive Lagrangian with boundary in M. And then you can look at the Hamiltonian isotopy class of all of these positive Lagrangians, which are Hamiltonian isotopic to lambda star, by like a Hamiltonian flow which preserves this fixed Lagrangian M. Okay, then this is also kind of a nice Frechet manifold, and you can repeat everything that we talked about so far in this kind of relative situation. So it's a Frechet manifold, and its tangent space is given by Hamilton, like functions on lambda, but now you don't need this kind of integral condition to normalize them. You can just say that they have to be 0 on the boundary. So when you have a Hamiltonian deformation which is 0 on the boundary, it just says that like it moves along inside of this Lagrangian boundary condition, M. Okay? So this normalization allows you for more flexibility in the definition of the functional. So in particular, like in the original situation, there was the C functional, which is similar to like the Mabuchi K energy in Kähler geometry. But so it's like a convex functional. But in this case, when you have boundary, you get another functional, which is more like the sort of Monge-Ampere energy, or it's related closely to the Aubin-Yau energy. So on the other hand, there's some, you need to assume that if you want to have geodesics existing in this relative situation, you need to assume the Lagrangian is imaginary special Lagrangian. Okay? The functional exists anyway, but it's not clear like what its properties are. And then you look at a special example of Cn, and basically you can take your Lagrangian boundary condition to be the phi-twisted conormal bundle of the, say you have this domain in Rn where you consider graphs of functions over this domain. You have some like sort of boundary condition, just a function on the boundary of the domain. You take a Lagrangian, which is the phi-twisted conormal bundle of the boundary, and this, like looking at Lagrangian graphs Lagrangian graphs which have boundary in M is just like the Dirichlet condition for the potential function U. So that was, I guess, the main thing. Thanks for asking. There's a bunch of questions here.
So this boundary problem is in terms of potential functions is a Dirichlet boundary condition. It's a fixed boundary.
Yeah.
So yeah, I was curious. There's this Donaldson picture which interprets Kähler metrics in a fixed Kähler class as like Lagrangian submanifolds of this twisted holomorphic cotangent bundle. I guess you know this picture. So do the Mabuchi metrics downstairs correspond to geodesics in your sense in this bigger picture, in this upstairs picture?
I don't think so.
I see.
I think that picture is a bit like the mirror of this picture. So, I mean, the truth is, like, Amitai, my PhD student who did a lot of these results with me, we searched for years for some interpretation of these geodesics in terms of holomorphic disks, inspired by this Donaldson picture. And eventually, like looking at Torr-Calabi-Yau manifolds, we could show that there couldn't possibly be a way of constructing them using holomorphic curves. I mean, it just didn't work. And then, like, out of sheer desperation, you know, we just sort of tried to see what there might be. And, you know, one day, Amitai came into my office and he said, you know, actually, we're looking at the wrong equation. It should be, but this is not maybe super surprising because, like, in a sense, holomorphic curves and special Lagrangians should maybe be mirror to one another.
I see.
Like complex submanifolds versus Lagrangian submanifolds.
Okay, thank you.
So.
So can you go a few pictures back where you started drawing this thing emerging out of the intersection? Yeah. So are you basically solving a Cauchy problem for the DSL? Or?
Well, I mean, what's happening is that I mean, you start some kind of like family, but this isn't like a time evolution equation. It feels like I mean, there's a lot of questions which come up about this about this family, which are kind of like what you'd want to know about like a time evolution. Like what happens is you follow this family along, it's going to develop singularities unless you have only like 2 intersection points. It's definitely going to develop singularities. And like there's a heuristic which says that these singularities should be something like some kind of surgeries, okay? And that you should be able to sort of go through them. So it sounds like it's some kind of parabolic equation, but it's not. It's a one parameter family of solutions to an elliptic equation. But maybe there are some things which we can like learn from the parabolic world about this one parameter family of solutions to an elliptic equation. I don't know if that addresses the question, but.
So in the case when in this case when space is a Cn cross Cn, what you did with the idea, and so you found the viscosity solutions, and so I guess you don't have a regularity yet for that viscosity solution.
No, although I think Yanir has a student who is working on this.
Also, it's that's in a flat case. In general, in a case of Calabi-Yau spaces, so the space is curved. Can you also have a kind of viscosity solutions?
So I mean, when the viscosity solution setup works very much on the basis of this kind of potential that you have. You can write your Lagrangian as the graph of the gradient of some function. But-
that I understand. But so this case, you have a kind of global section. But with viscosity solution, look at the geodesics. You just need to do it piece by piece. Piecewise, right? So maybe it's you can still patch them together to get the viscosity solution of a curved space.
So the potential is going to be C0, and then when you take its derivative to get the Lagrangian, in general, it's hard to even say like geometrically what it means, because you have like a C0 function, and then you take its derivative, and so it's, to make it geometric seems maybe some more ideas are necessary. I guess maybe on the top branch, so then the function is going to be convex always. So there's like there's different branches of this equation, just like in the special Lagrangian equation. And if you choose the top branch, then you're going to have a convex function, and then sort of at least almost everywhere you have a tangent space, and it might be possible to say something. But sort of again, maybe in this case of Lagrangian boundary condition, it's possible to do something like that. In general, it's hard to have like a convex function on a closed manifold or something, but maybe for this case with boundary, something can be done.
So in case of Kähler geometry, you have this space of Kähler metrics. Locally it's also given by if you fix the Kähler class, you just class the space is given by functions. It's kind of similar to the situation you are dealing with. And so here you use Hamiltonian functions. So in that case, in the case of Kähler metrics, so there is this theorem about you can approximate this matrix by Bergman type matrix. So it's kind of like a polynomial defined matrix. So then one way to find the weak geodesics is to first find the geodesic kind of a geodesic in the finite approximation. Then you take a limit, you get a kind of weak geodesic. In that case, maybe it's a C1 geodesics. So which can already can be used was very useful. How about in this case? Can you somehow take a kind of a finite dimensional approximation to get the kind of approximation bypass these harder regularity issues?
So I think there's something analogous, but maybe like in kind of in the spirit of mirror symmetry, some like arrows get reversed in a sense. So like in the case of Kähler metrics, you have like a map from some finite dimensional sort of approximation into the space of geodesics, or not into the space of Kähler metrics, and then you can have like a finite dimensional geodesic and approximates an actual geodesic. But in this case, we have like a map from the space of positive Lagrangians into some finite dimensional space, and this map sort of respects distances as long as you stay like quantitatively positive. So you can use it to say prove the non-degeneracy of the like path metric that you get from the Riemannian metric. But like in order to get a geodesic, you'd have to like somehow lift from like because the map from it's mapped from the space O to the finite dimensional approximation instead of the other way around. So you'd have to somehow take a geodesic in the finite dimensional approximation and lift it up to the space O. Not exactly sure how to do that, but maybe it could still work.
Do we have more comments or questions? Okay, if no, let's thank Jake again.